In modern implantology, the ultimate measure of long-term stability is the absolute preservation of crestal bone architecture. Preserving that bone becomes a challenge when the soft tissue surrounding the implant pulls away, leaving the architecture vulnerable. For decades, clinicians have operated under the assumption that early crestal bone resorption is an expected consequence of biological width remodeling. This assumption led the industry to accept 1 to 2 millimeters of initial bone loss as the baseline standard for a successful procedure. Looking closer at the cellular level suggests that this recession is a mechanical failure of soft tissue interface rather than an inescapable biological requirement. To stop crestal bone resorption, we have to look past the bone itself and interrogate the precise mechanics of soft tissue collar. The data that finally challenged the design of standard machined collar came from a series of landmark canine studies. Canine histological models serve as the gold standard for these observations because they allow us to see how tissue and implants interact within living biological system. This specific histological diagram outlines those findings. The overarching headline points to a specific objective: establishing a functional connective tissue seal in a living model. This suggests that true biological seal can be deliberately engineered. The core hypothesis tested here is whether specific surface microtexturing can override default wound healing to dictate how cells orient themselves. This set of histological slides illustrates how surface geometry influences the tissue response at the interface. To understand this influence, we first have to examine the industry baseline, the smooth machined titanium implant collar. Looking at the standard control model on the left, we can trace the specific mechanism of failure. Notice the purple cellular layer migrating down the side of the gray implant surface. This is the long junctional epithelium. Because titanium surface is chemically frictionless, there is nothing to stop the uninhibited apical migration of these cells. This long junctional epithelium acts as a weak, non-adherent tissue layer that fails to create a true functional seal. A smooth surface offers zero physical interlocking capability. It gives the soft tissue nothing to grab onto to resist that cellular downgrowth. Consequently, the standard machined collar facilitates deep soft tissue penetration, setting the stage for structural breakdown. The failure extends deeper than epithelium, continuing into underlying connective tissue. Below the epithelium, we see these pink connective tissue lines forming what is labeled as parallel fiber orientation. Because these fibers are forced to run parallel to the smooth implant, they cannot physically grip the titanium. This parallel alignment acts like a sliding barrier, offering no structural resistance to the descending purple epithelium above it. This lack of resistance leads directly to the red zone at the base, crestal bone resorption. The combination of migrating epithelium and non-gripping parallel fibers drives this outcome. As the invading biological width pushes downwards, the crestal bone resorbs apically to accommodate the encroaching soft tissue. Crestal bone loss around these machined collars is a direct cascade of failure that begins the moment connective tissue fails to catch. Interrupting this cascade requires an engineered alternative designed to stop it. laser lock microtexturing. Moving to the test panel on right, we see a different biological response. Notice the distant comb-like microchannels cut into the blue implant surface. These channels are precisely sized geometric constraints engineered to force a specific cellular behavior during the healing phase. Look closely at how the pink connective tissue fibers physically interlock with these blue microchannels, establishing a perpendicular fiber attachment. Unlike the machined control, these fibers grip the textured surface, creating a perpendicular anchoring system. This perpendicular physical interlocking provides the mechanical tension required to establish a true functional connective tissue seal. Securing this connective tissue base initiates a series of cascading effects on the aggressive tissue layers above it. Look at this exact junction where the descending epithelium meets the microtexturing. The label reads epithelium stopped. There is a rigid boundary separating the purple cells from the pink fibers. Because the connective tissue fibers are anchored perpendicularly, they act as a physical and biological barrier against anything trying to migrate past them. The downward migration of the junctional epithelium is definitely halted at this microtexturing margin. The implant physical geometry successfully overrides the default wound healing response, blocking the soft tissue invasion before it can reach the bone. Weaving these two distant biological responses together reveals the difference in clinical outcomes. This study directly compares the machined control with the laser log test. The bottom right displays a thick green bone preservation at the collar. Microtexturing creates a functional seal shielding underlying crestal bone. A horizontal line drawn from this preserved bone to the left panel reveals a severe contrast. The gap between that line and the receded red bone demonstrates the volume of hard tissue sacrificed when a machined smooth collar is used. The canine model proves that biological width is a variable that can be actively engineered and controlled through surface topography. These histological findings directly impact our expectations for surgical predictability and long term aesthetic outcomes. Initial crestal bone loss represents a failure in interface engineering rather than an inescapable biological requirement. The clinical standard must shift away from passively accepting initial bone resorption toward demanding a precise perpendicular connective tissue attachment at the collar. True long term stability is dictated by a single step engineering a mechanical connective tissue seal before the underlying bone is ever engaged.